we're going to talk a little bit about splines. Again, my name is Scott Hansel, and I'll be your tour guide for this particular CES. And we're going to talk about splines and their applications. We're going to talk a bit about the math and spline complexity and vocabulary throughout the presentation. And then we'll do a little summary here at the end to make sure that I have addressed everything that you see here. Okay, so the first thing we're going to talk about are some applications for splines. Splines are used throughout the design industry. Here are just a few of them. We have automotive, where we use splines to create those shapes that can't be addressed with a simple line or an arc. And those kind of applications include body panels, lenses, um, wheel design, and also interior components. We also see splines being used in body panels on planes, all right, in the aerospace industry, lenses, and also interior components there. And again, these are shapes that can't be addressed merely with straight lines and arcs. And last but not least, we have organic shapes. There's a lot of talk about organic shapes and their use. And really, organic shapes are just things that basically occur in nature. But in order for a software package like NX to use organic shapes, we need to use things like splines, which give us much more creative authority, if you will, over the shapes that we are designing. So with that, let's talk a little bit about the math. Now, one of the things that is associated with splines is things like complexity and degree and so on. So we're going to start with the simplest of the splines, or curves as they're referred to in NX, and that is a line. And a line is a 1-degree uh, object, okay, which means it needs to be defined with 2 points, okay, and we know the old adage, right? The shortest distance between or an object to another object is defined by 2 points. And also the line has no curvature, okay? Next, we have the conic. Now, conics you're probably familiar with in the terms of circles and arcs, but there's also things like ellipses, parabolas, hyperbolas, things like that. And these are 2-degree curves, or 2-degree splines if you wish. And when we talk about a 2-degree curve or spline, that needs to be defined by 2 points. So if you'll notice, there's a little pattern developing here. If it's a 1-degree spline, we need 2 points. If it's a 2-degree spline, we need 3 points. So you'll notice that it progresses up. And then last but not least are the splines themselves, or what we refer to as splines typically, which is 3 degrees or better. All right, and at 3 degrees, we need 4 points. At 4 degrees, we need 5 points, and so on. All right, and the biggest thing with a spline is that it does allow a reversal of curvature. And most applications that we're going to see are done with 3-degree to 7-degree splines. Now, NX allows us to go up to 24 degrees for a spline, but understand that as degrees go up, so does spline complexity, and that can have a significant effect in regeneration times or the complexity of a part file with several splines or multiple splines, okay? As the part file goes up and we're using a higher degree splines, we can see a significant difference in regeneration. And again, this is because this is math-based. So if we go back up to the line for just a second, we know there's a mathematical statement that's associated with it called y equals mx plus b. And it makes it a 1-degree spline because if we think of the power of x in that particular sentence, it is 1. Okay. If we look at a conic, and a simple math explanation there for a conic would be like the basic circle, okay, which is x squared plus y squared equals 1. All right, and we know that's a 2-degree based on the power of the variables in there, x squared, y squared, okay, 2-degree. And then the last one down here for splines, those are even more complicated. If you remember back to your algebra class, you probably graphed curves, okay, and one of them might be an x cubed equals y, okay, something to that effect, where you would uh, graph the line, all right, based on that cubic expression, or x to the third, and so on and so forth. So anything over 3 degrees is going to allow a reversal of curvature, and just understand that the complexity goes up with the math associated with it. So I'm going to use here the Studio Spline dialog that you're going to see in NX. And again, we're not necessarily going to create any splines today, but we are going to talk about how they are created. And up at the very top of Studio Spline, you're going to see that you have a pull down, and it allows you options for creating splines. One is called through points, one is called by poles. When we're using through points, the biggest thing to remember here is that you're going to define the spline by points that you actually want it to pass through. Okay, so there we can actually pick defining geometry and actually create the spline through it. Okay, the other option that we have is a by poles option. Okay, and the by poles option allows us to create a framework, if you will, that helps define the shape of the spline. Here I've got just a simple parabola being shown, and you'll notice that the poles, the first and last, the spline passes through, but that second pole that you see up there just creates the shape, if you will, or a shape that the spline must conform to. Okay, so it doesn't have to pass through it, it just defines the shape. Okay, now what I will do also is about halfway down that dialog box, you're going to see something that shows parameterization and a degree. This is where you can set the complexity of your spline, but just understand as you pick the degree, you also need to define points associated with that degree. So here you can see that it shows a 5-degree for the spline. Understand that you're going to have to pick at least 6 points in order to create that spline. Next, we'll take a look at, try that again, there we go. All right, if we take a look at a spline, there's a couple of things that we need to note about splines, and this really goes to how we can use splines to help define transitions. Okay, so if we think about maybe another spline that would be attached to this one on one end or the other, and we want to create a transition between those splines that helps us define a shape. So what I've got here is a spline, and I need you to imagine a couple of objects that might be attached to the ends of those, or the end of that spline. And we'll talk about transitions that we can deal with. In the Studio Spline, you'll notice that there is a list of continuity that we can use for splines. And I just want to go through these. You will see the G0, G1, G2, G3 continuity types. You'll see them in several operators within NX. And just understand that they work the same way, but you might be using a sheet instead of a spline. You might be using a blend, things like that, but you do have the ability to control continuity. So what does that actually mean? Well, G0 is considered a touch constraint. Now with a touch constraint, all that means is that the endpoints of the defining object and the endpoint of the spline itself need to touch. So that means that we could actually have a hard corner being our continuity type. All right. Underneath that, you see G0 or G1, excuse me, which is tangency. And that considers poles 1 and 2. So if you look at the illustration between 1 and 2, you're going to notice a straight line, okay, which is that the difference between pole 1 and pole 2. So that straight line means that we're going to have objects that are going to intersect one another using tangency. Okay, so just a straight line, a smooth transition, that's all. And all we're doing is we're getting that tangency at that point. That is the consideration. If we look at G2, this is called curvature. All right, when we look at curvature, that considers poles 1, 2, and 3 in this case. So if we're going to use a continuity, or excuse me, a curvature constraint, we need to have a spline that has the ability to follow that. All right, so we need to create a spline that's a little more complex. All right, so curvature constraint takes 3 of those points, or those poles, excuse me, and it uses those to help define the curve. And what you're going to notice is that when you're using curvature, it's going to consider a bit more of that curve. It's actually going to consider how it's created radially, if you will, or how that comes about. And if you remember the conic that I showed you a couple of slides back, that used 3 poles, all right, to do that. So that gives you an idea there that we're actually considering curvature. And last but not least, we'll talk about G3, which is flow. And flow considers the first 4 poles in this particular spline. Now, when you use flow, all right, understand that you are getting a bit more information about the spline, all right, and the consideration for that transition. And this plays an important role when you're looking at creating transitions from one object to another, all right, and that's what this is all about. So we have basically a hard corner all the way through a much smoother transition from one object to the next. This also allows us to give a bit more shape to our transition, so we can do things like create highlight lines. We can do things like accentuate the shape a little bit more by the fact that we have more poles to deal with. So if I am going to create a transition from one defining object to another using a spline, understand that if I bounce the continuity type to G3, in this case, right, we have 4 points being considered on one line and 4 poles on the other end. Should be poles for both ends, excuse me. So we would need to create at a minimum, if I've got 8 poles, that's a 7-degree spline, okay? So if we want that on both ends, we're going to use all 4 or all 8 poles, 4 on each end. So just understand that as we bump up the continuity type, we may have to create, or we will have to create, more complex splines. So I'm going to go on here just to kind of give you an idea of transitions that you might see using splines. So here, what I've got are a couple of, or 3 actually, examples using flat sheets and then using different transitions. And you can see the reflections change from one to the next. So if we look at the first example there on the left, here we're using a tangent constraint. So if we had used some splines to help define that transition from the top sheet to the bottom sheet, we have that curved transition in between. If we're using tangency, you can see that we've got a much more flushed out kind of highlight there on that surface. And in some cases, when you see it, it can actually look like a hard line where it actually makes that transition from the flat sheets into that curved surface. It's kind of hard to imagine, but you can actually see a line. And if you kind of look towards the bottom where that curved surface ends, you'll notice that there's a little bit of shading that shows up that almost looks like a defined line, or that they're not actually making a smooth transition. It is a smooth transition, but when light is used, it'll give an interesting effect. If we look at that second one, we're actually using a conic in this case, like a parabola, and making that transition. So here we could actually use something that has a little bit smaller radius, okay, in the middle, and that gives us a much more defined line. So as we bump up complexity and we can change the shape of that spline to create those transitions, you can see that we have a lot of control where and when those highlight lines occur. And that last one that you see there, if we were to use curvature as a constraint, uh, defining our spline, we can actually consider that surface a little further along, and you can see where we have a very nice defined highlight line. Now, you may ask where highlight lines come into play. Well, all you have to do is look at an automobile, for instance, and take a look at it from different angles. And when you see those reflections off the surfaces, you will see very defined highlight lines and shadows, which are desired options for a particular body style, for instance, and somebody wants to pull out a particular feature or have the eye drawn to a particular aspect of those exterior surfaces. So this just gives you an idea where we might be able to use splines to define surfaces and actually create the aesthetic effect that we want. So here we are. So we've looked at splines, we've looked at some of the math associated with them, and we've looked at some basic applications for splines. So you can see it's a very powerful tool. But again, there's a balance, all right? And that balance is in terms of complexity, okay? And we talked a little bit about the math associated with that and how the complexity of a spline is basically defined by mathematics, okay? So the vocabulary that we talked about here, we talked about poles, we talked about points when defining a spline, we talked about uh, continuity, G0, G1, G2, and G3. Okay, so we had touch, we had tangency, we had curvature, and we also had flow. All right, so there we are. It's again a brief explanation about splines and the math and their application. So at this point, I'll relinquish the floor to questions, but thank you for listening so far, and I hope this was helpful.
All right, so our first question is, I'm not sure I understand why higher degree splines can slow down processing. Can you please explain further?
Okay, it's a good question because again, a lot of this looks like it's magic, but it's not. All right. The CAD systems use mathematics to calculate several different things. So let's say we take a file and we've got 3 splines in it of 3 degrees, okay, or we take a file that has 150 splines in it of 3 degrees. You are going to notice a difference in regeneration, maybe not as great because they're 3 degree splines, but if we turn that around and let's say we make them 15 degree splines, that's going to require a much more complex mathematical sentence to describe it. So if we have those 150 curves at 15 degrees, it's going to create more complex mathematics, and therefore it's going to create a longer regeneration time.
All right, our next question is, can the degree of a spline be changed once it's created?
Yes, degrees of splines can be changed. We could, for instance, go right back to the dialog box that I was showing you before, and we can click on that spline and actually change the degree within that dialog itself. So once it exists, we can change the degree. So if we find that a 3-degree spline is not giving us the results that we want, we could always change it to a 5-degree if necessary, or if we don't need anything quite so complex, we could always bump the degree down.